This is Hypatia. She lived from 370 to 415 AD. The Greeks discovered conic sections sometime between 600 and 300 BC. By the beginning of the Alexandrian period, enough was known about conics for Apollonius, who lived from 262 to 190 BC, to produce an 8-volume work on the subject. Later, toward the end of the Alexandrian period, Hypatia wrote a textbook entitled On the Conics of Apollonius. Her death marked the end of major mathematical discoveries in Europe for several hundred years. The Greeks were largely concerned with the geometric properties of conics. It was not until 1900 years later, in the early 17th century, that the broader applications of conics became apparent. Conics then played a prominent role in the development of calculus. And sadly, conic sections are left out of Algebra 2 and Pre-Cal because for some reason they're deemed not important enough to study. Well, they are. They are important enough to study, and we do a lot with them in calculus. So each conic section, or simply conic, can be described as the intersection of a plane and a double-napped cone. Notice in figure 10.1 that for the 4 basic conics, the intersecting plane does not pass through the vertex of the cone. When the plane passes through the vertex, the resulting figure is a degenerate conic, as shown in figure 10.2. So when I take my double-napped cone and I intersect a plane through it that is perpendicular to the altitude of the cone, I get that intersection is a circle. When the plane is slanted and goes through the base, we get our parabola. When the plane is slanted but does not go through the base, we get our ellipse. And when the plane is perpendicular to the base, I get my hyperbola. Our degenerate conics occur when our plane intersects at the point, when it goes through the vertex here but intersects the outside, and when it is perpendicular to the base going through the vertex, and I get the 2 intersecting lines. Now, there are several ways to study conics, but this is a general form, second degree, x is squared, y is squared. You may or may not have a product xy. A third approach, in which each of the conics is defined as a locus or a collection of points satisfying a certain geometric property, works best. For example, a circle can be identified as the collection of all points x, y in a plane that are equidistant from a fixed point, hk. The locus definition easily produces the standard equation of the circle, x minus h squared plus y minus k squared equals r squared. You should recognize that. A parabola is the set of all points that are equidistant from a fixed line called a directrix. Here's our directrix. And a fixed point called the focus, which is not on the line. The midpoint between the focus and the directrix is the vertex. The line passing through the focus and the vertex is the axis of the parabola. Now, notice that we call this distance P, so this distance is P. The parabola is a set of all points equidistant from the focus and the directrix. So this point here, which is D1, this distance from the line, is also the same distance from the focus. This point here, this distance equals that distance, and so forth. That is how a parabola is formed. So the standard form for the equation of a parabola is x minus h squared equals 4p times y minus k. Let us remember, p is this length right here. This is a vertical parabola. It has a vertical axis, okay? And the directrix is the line y equals k, the y coordinate of the vertex, minus p, takes us down to there. The equation for a horizontal parabola is y minus k squared, again, equals 4p, x minus h. In general, I just want to talk about the shape and the equation from the standard form of the equation. If we look at this, we can see that this is not in a standard form. What could I do to get it? Well, I can go through all this process, or I can multiply everything by 2. That is going to give us 2y equals negative x squared minus 2x plus 1. And if I want to make this so that I have x minus h quantity squared, I can see that what I would need to do is certainly factor out the negative, and I'm also going to subtract the 1 over here. So I'm going to write this as 2y minus 1, moving that over here. Factoring the negative out gives me x squared plus 2x plus blank. And if I add something here, I have to add it over here. What do I need to add here to complete the square? I need a +1, but I didn't really add a +1. I really added a plus times a minus, a -1, so I'm going to add a -1 over here. So that's going to give us 2y minus 2 equals negative x plus 1 quantity squared, which gives us, when we factor out the 2, y minus 1 equals negative x plus 1 quantity squared. So I can take this negative and write this as negative 2y minus 1 equals x plus 1 quantity squared. Here's my 4p. P is -1/2, which tells me my parabola is opening in a negative direction. Since the x is squared, we know it is a vertical parabola. Think of the x like that. So my vertex is at -1, 1. And p equals -1/2 means that from the vertex, down 1/2 gets me to the focus, and up 1/2 gets me to the directrix. And you can see a nicer drawing over here. So let us remember, if the x is squared, we have a vertical parabola. If the y is squared, you have a horizontal parabola. I would encourage you to read this page. There's some interesting properties about parabolas that I won't go into here, but they're pretty cool. This is Nicholas Copernicus. He began to study planetary motion when asked to revise the calendar. At that time, the exact length of the year could not be accurately predicted using the theory that Earth was the center of the universe. Lots of things happened there. So Copernicus claimed that all of planets, including Earth, revolved around the sun in circular orbits. Although some of Copernicus's claims were invalid, the controversy set off by his heliocentric theory motivated astronomers to search for a mathematical model to explain the observed movements of the sun and planets. The first to find an accurate model was the German astronomer Johann Kepler. He discovered that the planets moved about the sun in elliptical orbits, with the sun not as the center, but as a focal point of the orbit. The use of ellipses to explain the movements of planets is only one of the many practical and aesthetic uses. As with parabolas, you will begin your study of this second type of conic by defining it as a locus of points. Now, however, there are two focal points instead of one. An ellipse is the set of all points in a plane, the sum of whose distances from two distinct fixed points called foci is constant. The line through the foci intersects the ellipse at 2 points called the vertices. The chord joining the vertices is the major axis, and its midpoint is the center of the ellipse. The chord perpendicular to the major axis is the minor axis of the ellipse. Here are your two foci. Here is your major axis. Here's your minor axis. The distance from the center to the vertex is A. That's always longer than the distance from the center to the endpoint of this chord, which we call B. The distance from the center to the focus is C. What makes the ellipse is that this distance and this distance is constant when I add them together. So if I come here and I draw this line segment and this line segment, guess what? That length plus that length will equal this length plus this length will equal this length plus this length. That's how the ellipse is formed. To find your C, you will notice that here is my A, here is my B. You can see that C has to be less than A. And so your C squared is A squared minus B squared. Now, the standard form of an ellipse is x minus h quantity squared over a squared plus y minus k quantity squared over b squared equals 1. That is a horizontal ellipse as drawn in the diagram there. And the vertical ellipse has the a squared under the y squared term. And the foci always lie on the major axis. So one of the things you would have done in pre-cal and algebra 2 possibly is finding the center and the vertices and the foci of an ellipse given an equation. Well, let us remember, we have to have x minus h quantity squared, y minus k quantity squared, and the equation must be equal to 1. So the first thing that we're going to do is group together our x's and our y's. 4x squared minus 8x plus a blank plus y squared plus 4y plus a blank. And I'm going to move that 8 over, and I'm going to do plus a blank and plus a blank. Now, in order to complete this square, we need to factor out the 4. And factoring out the 4 gives us x squared minus 2x. So to complete that square, I need to add a 1. But I didn't really add a 1. I added a 4. So looking at this, I don't have anything to factor out to get my coefficient of my y squared term to be 1. But I can group y squared plus 4y becomes y plus 2, the quantity squared. So I need to add a 4 here. Now, notice I added a 4 to complete this square. I added a 4 to complete this square. So I have to add 4 on both the other side of the equation. And that is going to give me this equals 16. And what's the next part? We have to have this equal to 1. So now I have 4x minus 1 squared divided by 16 plus y plus 2 squared divided by 16 equals 1. And we need to have on top no coefficient of the x squared term. It needs to be down here. So 16 divided by 4 gives us 4. So here we have this. Now what do we see? A squared is the bigger one. So a is 4. B squared is the smaller one. So b is 2. What is my center? The point 1, negative 2. So I am going to go from 1, negative 2, up 4 to get to that vertex, and down 4 to get to that vertex. And I'm going to go right 2 to get to this point, and left 2 to get to that point. So here I have my minor axis, which is a length of 2 times 2, 4, and my major axis, which is a length of 2 times 4, 8. C is the square root of a squared minus b squared. A squared minus b squared. So 2 squared root of 3. Square root of 3 is about what? 1.7. 2 times 1.7 is 3.4, which is less than 4, which is good because it needs to be. And there is your nice, beautiful ellipse. Again, a nice little example about the orbit of the moon around the Earth. Notice that the Earth is not at the center of a circular orbit. This length from here to the circle is called the perigee. This is the apogee. Nice little information there. Now, how narrow an ellipse is determined by eccentricity, and that is the ratio of C to A. Now, let us remember, C is always less than A. Why? Because it lies on the same axis, the major axis. Here's my center. A goes to the vertex of the ellipse, and C goes to the foci, and the foci have to lie inside the curve. So eccentricity is formed by the ratio of C over A. It is always less than 1 for an ellipse, because why? C is less than A. If C equals A, then what you have is a circle, not an ellipse. All right, so we have A goes from the center to the vertex. C goes from the center to the foci. And you can see that the ratio of C to A would certainly be less than 1. And this is what's interesting. For an ellipse that is nearly circular, the foci are close to the center and the ratio C to A is small. And for an ellipse, elongated ellipse, the foci are close to the vertices and the ratio is close to 1, as shown in figure 10.12. So the definition of a hyperbola is similar to that of an ellipse. For an ellipse, the sum of the distances between the foci and a fixed point is fixed or constant, whereas for hyperbola, the absolute value of the difference between those distances is fixed. So a hyperbola is the set of all points in a plane for which the absolute value of the difference between the distances from two distinct fixed points called foci is constant. The line through the two foci intersects the hyperbola at 2 points called vertices. The line segment connecting the vertices is the transverse axis, and the midpoint is the center. One distinguishing feature of the hyperbola is that we have 2 separate branches. Again, notice that my equation looks very similar to the ellipse, except there's a subtraction sign. Also, notice that a squared, the larger distance, is with the positive term. Also, c squared is a squared plus b squared. That looks like Pythagorean theorem. Well, if we look here, notice that c takes you to the focus, and the focus lies inside the curve, just like the focus of an ellipse was inside the curve, just like the focus of a parabola is inside the curve, okay? But to graph a hyperbola, what we want is that distance A and that distance B from the center, and we want to create our box. When we connect the diagonal with a line, that is called an asymptote, and your branch of your hyperbola gets very close to that asymptote, but does not touch it. Okay? So the key in sketching your hyperbola is to sketch that box, then draw the asymptotes, which are dotted lines, and then sketch your branch of your hyperbola. So sketch the graph of the hyperbola whose equation is this. Okay, first thing is we do have two squared terms with opposite signs. It needs to be equal to 1, so we're going to divide through by 16, which gives us this. Let us remember, a is not necessarily the larger constant like in the ellipse. It is the one that is positive. So a squared is 4, so a is 2. B squared is 16, so b is 4. My center is the point 0, 0. So we are going to go, and this is a horizontal hyperbola because the x squared is positive. So a is going to go right and left, b is going to go up and down. From the center, right 2, left 2. Up 4, down 4. Sketch in the asymptotes, and your vertex of your hyperbola lies on this box here and here, and it goes close to the asymptote but does not touch. There you go. Now, what about eccentricity? The eccentricity of a hyperbola is once again given by the ratio c over a. Notice that c lies inside the curve. C is bigger than a. Because c is bigger than a, for hyperbolas, it follows that e is greater than 1 for hyperbolas. If the eccentricity is large, the branches of the hyperbola are nearly flat, like this. If the eccentricity is close to 1, the branches of the hyperbola are more pointed, like this. And again, this is a really nice example of how hyperbolas have practical use in everyday life. What I have to say about the conic sections is there's a lot of real-life applications, and it's unfortunate that this has been de-emphasized in mathematics. But when we get to calculus, there's a lot that we can do with hyperbolas, ellipses, and parabolas. So you just need to recognize those general forms and what kinds of shapes they make. So you can see here, this is a parabola. It is the x, which is going to be squared, and it's opening up, so my 4p is going to be positive. Here is an ellipse. We are elongated in the x direction, so a squared is going to be under the x squared. This is a horizontal hyperbola, so the x squared term is positive. We would have to find our a and our b. Our a is 3. And we're going right and left, so this means it is a horizontal hyperbola. Here is a vertical hyperbola. Our a is 4, and it's going up and down. Again, we'd have to know a little bit more about finding c. In general, the only thing I would assign is that you match these equations here with their graphs, knowing basic properties of those equations. So you should do that. Okay, now you're ready, once you've done that, to watch the next video.